We are here to help.
Significant digits or figures are the digits in a value, often a measurement, that contribute to the degree of accuracy of the value. We care about the number of significant digits in a value to ensure that the rest of a computation is not any less precise than the values being used. There are a few rules we follow when determining which digits in a value are significant or not. Let's look at some examples to get a better idea of how the rules apply. Example 1. Consider the value 1000.4. By rule number 1, the digits 1 and 4 are significant since they are both non-zero. Notice that there are 3 zeros between them. By rule number 2, these are also significant, so this value has 5 significant digits. Example 2. Consider the following value 0.00900. By rule number 1, the 9 is significant. And by rule number 3, the 2 trailing zeros after the 9 are also significant. Therefore, this value has a total of 3 significant digits. Example 3. Consider the number 70,000. By rule number 1, the 7 is a significant digit, but the other digits are not. This is because the zeros after the 7 don't tell us if this number has been approximated to the nearest 10,000, 1,000, or any other place value. So the 7 is the only digit which gives us information about the accuracy of the number. However, if we add a decimal 0 to the end of the value, by rule number 3, the 0 after the decimal would be significant. And by rule number 4, the zeros between the 7 and the decimal are also all significant, giving us a total of 6 significant digits. Multiplying and dividing while maintaining significant digits. When multiplying and dividing measurements, our result must be as precise as our least precise measurement. This means that our result must have the same number of significant digits as the measurement with the least number of significant digits. For example, suppose we needed to calculate the area of a rectangular yard. The length is 12.72 meters, with 4 significant digits. The width is 10.3 meters, with 3 significant digits. Since we are multiplying these values to obtain the area, our final answer must have as many significant digits as the value with the least number of significant digits. 10.3 has the least number of significant digits between these two measurements, so our final answer must also have 3 significant digits. We first calculate the area without rounding, and we get 131.016 meters squared. This value has 6 significant digits, but our answer must only have 3. In order to keep 3 significant digits, we must round to the nearest square meter. And our final answer will be 131 meters squared. When adding and subtracting measurements, we follow a slightly different rule. Suppose we want to add 5.67 and 2.4. 5.67 has 3 significant digits and is measured to the nearest hundredth. 2.4 has 2 significant digits and is measured to the nearest tenth. The precision of our result is based on the least precise measurements used in the calculation, which means that our result cannot have more decimal places than the value with the least number of decimal places. If we add these two measurements without rounding, we get 8.07. Since our least precise measurement in our calculation is 2.4, with 1 decimal place, our result must also be measured to the nearest tenth. Thank you for watching. We are here to help.